One evening in the spring of 1905, Albert Einstein, then a mere patent clerk in Bern, after trudging through his day's work, decided to board a tramcar on his way home. Einstein would often wrap up his work as soon as possible to contemplate the truths of the universe in his free time. It was one of these thought experiments he devised on that tramcar that revolutionized modern physics forever. While receding away from the Zeitglocke clock tower, Einstein imagined what would happen if the tramcar were receding at the speed of light. He realized that if he were to travel at 186,000 miles per second, the clock's hands would appear to completely freeze. At the same time, Einstein knew that, back at the clock tower, the hands would tick along at their normal pace. For Einstein, time had slowed down. This thought blew his mind. Einstein concluded that the faster you move through space, the slower you move through time. How is this possible? Einstein's work was heavily influenced by two of the most iconic physicists of all time. First, there were the laws of motion, discovered by his idol, Isaac Newton, and second were the laws of electromagnetism, laid down by James Clerk Maxwell. Newton's laws insisted that velocities are never absolute, but always relative, so that their magnitudes must be appended by the phrase, with respect to. For instance, a train travels at 40 kilometers per hour with respect to someone at rest. However, it only travels 20 kilometers per hour with respect to a train traveling 20 kilometers per hour in the same direction. Or, it travels 60 kilometers per hour with respect to another train traveling in the opposite direction at 20 kilometers per hour. This is also true for the velocities of Earth, the Sun, and the entire Milky Way galaxy. On the other hand, Maxwell found that the speed of an electromagnetic wave, such as light, is fixed at an exorbitant 299,792,458 meters per second, regardless of who observes it. However, Maxwell's notion seems incompatible with Newton's notion of relative velocities. If Newton's laws are truly universal, why should the speed of light be an exception? This presented Einstein with a daunting dilemma. This conflict between the ideas of Newton and Maxwell can be demonstrated with another of Einstein's brilliant thought experiments. Einstein imagined himself on a train platform witnessing two lightning bolts strike on either side of him. Now, because Einstein stands precisely in the middle of the two strikes, he receives the resulting beams of light from both sides at the same time. However, things get more complicated when someone on a passing train views this event while whizzing past Einstein at the speed of light. If the speed of light conforms to the rules of relativity, then the person on the train wouldn't witness the lightning strikes simultaneously. Logically, the light closer to the man on the train would reach him first. A measurement of the speed of light made by both men would differ in magnitude. This would contradict an apparently fundamental truth of the universe. Einstein had to make a difficult choice. Either Newton's laws were incomplete, or the speed of light was not a universal constant. Einstein realized that the two notions could coexist with a small tweak in Newton's laws. To get rid of the discrepancy in the measurements, Einstein suggested that time itself, for the man on the train, must slow down to compensate for the increase in speed, such that the magnitude remains a constant. Einstein called this absurdity time dilation, and his newfound theory special relativity. Newton believed that time moved unflinchingly in a single direction, forward. Einstein, however, had just realized that time stretches and contracts, varying with velocity. Due to its malleability, time, like space, deserved its own dimension. In fact, Einstein claimed that the two were one and the same. Together, they formed a four-dimensional fabric or continuum called space-time, upon which the mundane events of the universe would unfold. Einstein suggested that massive objects like the Sun didn't pull bodies like Earth with a mysterious, inexplicable tug, but rather curved the fabric of space-time around them, forcing Earth to fall down into this steep valley. A highly simplified analogy is the dip in a trampoline made by the bowling ball. If a marble were placed on that trampoline, the marble would immediately roll towards the bowling ball in the center. This is also true for Earth's gravity. We are pinned to the ground because space, so distorted by the Earth's mass, pushes us down from above. However, the slump in the fabric around Earth is not uniform, and Earth's gravity grows more intense as we move towards its center, where the curvature is at a maximum. Therefore, like the marble on the trampoline, an object that falls towards the Earth accelerates as it races towards the center of the planet. It falls faster when just above the surface than it does, say, when it is slightly above the atmosphere. But hey, according to special relativity, the faster you move through space, the slower you move through time. This means that time runs slower on Earth's surface than it does above the atmosphere. Now, because different planets have different masses, and thus different gravitational strengths, they also accelerate objects at different rates. As we have learned, this means a variable passage of time. This is what happens in the movie Interstellar, when the protagonists land on a planet in the proximity of a black hole. The gravity on the planet is so severe that 1 hour on the surface is equivalent to 7 years on Earth. To understand how motion affects time, let's consider the simplest timekeeping mechanism. A second passes each time the photon is reflected. Let's imagine two people, one in a spaceship slightly above Earth's atmosphere, and the second on top of a small hill just above the Earth's surface. Both are watching a man fall from space towards the ground. Let's say that the falling man is carrying the photon clock explained a moment ago. What do each of the two men observe as the man falls past them? What they observe is eerily similar to what a stationary person would observe when watching a ball bounce in a moving train. As the man falls from space, the light in his clock would appear to move in triangles to the two observers. This would mean that the light travels a longer distance, consequently stretching the duration of a second. It is obvious that the length of triangles the light traces, and therefore the duration of a second, is proportional to the velocity of the falling man. When we recall that objects closer to the center of the planet fall faster, we can determine that time would appear to pass slower to the man on the hill than it does to the man in the spaceship above. Of course, the difference is infinitesimal. The difference between the time measured by clocks at the tops of mountains and at the surface of Earth is a matter of nanoseconds. Time dilation affects every clock, whether it relies on basic electromagnetism or a complex combination of electromagnetism and Newton's laws of motion. In fact, even biological processes are slowed down. Yes, that's right. Your head is slightly older than your feet. In 1895, a 16-year-old boy imagined himself chasing a beam of light. This thought eventually changed the world forever. The boy's name was Albert Einstein. So what really was that thought? And how could one thought change the world so thoroughly? Well, in this video we're discussing Einstein's theory of relativity, and more importantly, how he got there. We cannot start talking about Einstein without discussing classical physicist Sir Isaac Newton. In 1687, Newton published his book Mathematical Principles of Natural Philosophy. In the book, he described history, laws of motion, and the law of gravity, His book is considered one of the most important writings in the history of mankind. After watching an apple fall, he asked himself a question. If the apple falls, does the moon also fall? This question led him to discover the law of gravity. According to his law of gravitation, every object in the universe enacts its own force of attraction on another object. And this force is the reason why we're stuck on Earth, why the moon orbits the Earth, and indeed why the universe exists. But that didn't answer all of Newton's questions, like, why do objects attract each other? What is the source of gravity? And why does Mercury's orbit jiggle? The rest remained a mystery until the era of Albert Einstein. In 1915, Einstein published his theory of general relativity, or in other words, his theory of gravity. In this theory, Einstein explained gravity and its source. He answered all the questions that Newton couldn't, like Mercury's precession. Let's take a step back to 1905 to truly grasp where these different pieces of the puzzle come to life. This year, Einstein published his theory of special relativity. It deals with the speed of light and the motion of objects. It was fine with non-accelerating objects, but the theory did not apply when gravity was present, or if the object was accelerating. He couldn't quite figure the rest out, until one fine day in 1907, he was observing a window washer on a ladder and had an epiphany. He thought about what he would be experiencing while falling. He imagined himself there and realized that while falling, the ground would not be pushing him, so he would be in a free fall. That put some of the pieces together, but still he wasn't fully finished. He began to think about falling again. This time he imagined himself in a room with no windows. On the surface of the Earth he would weigh whatever you weighs now. But imagine if the room was in a spacecraft, moving in an upward direction and with the same 9.8 meters per second squared as here on the ground. In that moment, if you were to weigh yourself, you would weigh the same as you do on Earth. Einstein realized that the observer would not be able to tell if he is on a spaceship or on the surface of the Earth. That is because he would be moving at the exact same rate of acceleration. There would be no way to tell the difference. This phenomenon is called the equivalence principle, which states that an object that is accelerating free of any gravitational pull is essentially no different than the same object that is stationary, but affected by gravity. In other words, something moving in space with no gravity has the same mass as something on Earth that is not moving. In his special theory of relativity, he could only deal with non-accelerating objects and the speed of light. Let's pause here for a second. This means that at that point, he knew how to unify his theory of special relativity with gravity. Luckily, he didn't stop there. He did another thought experiment. This time he imagined what would happen if he pointed a laser beam from one side of the room towards the other. If the room were in a spaceship that was moving upwards with the same acceleration rate as Earth, the height of the beam would slightly be lower on the other side of the room. As the floor moved up, it turned the light and caused it to bend down. But this principle only applied in space. When he thought about the same experiment on Earth, the light would appear to be straight. Of course, these two scenarios only happened in his brain. Let's just take a brief moment. From what it is to its impact on the world at large, join us as we explore Einstein's theory of relativity and explain it so everyone can understand it.
So where do we start with something as big and said that no speed in the universe could be an absolute? But then Maxwell counters this by saying one.
I still lose sleep over this fact.
Okay.
I still lose sleep over it. And I want you to lose sleep too. I don't want to be the only one staring at the ceiling at night.
I'm going to tell you, a lot of things already beat you to that.
Oh, sure. I mean, the asteroid strike that could happen,
Yeah,
or the
exactly.
right, or the global warming, or all right.
Yeah.
So here it is. You may remember, or you may have heard, that Einstein's relativity,
Right.
more specifically, you learn this in special theory of relativity, where the faster you move,
Right.
the slower time ticks for you
Right.
as others view it.
Relative
okay?
to the observer.
Relative to the observer, correct. You don't know anything's happening.
Right.
Your clock still ticks as far, you still got your heartbeat, all of this. Okay, so this is not a physiological thing. It is an actual property of the fabric of space and time under those conditions.
Wow.
Okay?
That is fascinating.
It is. It's completely fascinating. It's completely. So I watch you fly by, and the faster you go, the slower time ticks for you. Okay?
But my time stays the same.
To you.
To me. Right.
To you. So not only does speed do this, also the strength of a gravitational field will have this same effect on you. The stronger the gravitational field is, the slower time ticks for you. And that wasn't formulated until his general theory of relativity 10 years later. That took a lot more math and deeper insights into the universe.
But once again, it makes sense because you're dealing with the fabric of space-time.
It's the fabric of space-time, correct.
Wow, okay.
But initially, when formulated, you're thinking it's just because you're moving.
Right.
But it's actually way deeper than that. And that's why that one, oh, by the way, his original special theory of relativity was not called that. The title of the research paper was On the Electrodynamics of Moving Bodies.
What?
Okay, that was the title. We would later call it the special theory of relativity because it was a special case of what would later then be called the general theory of relativity. While we're there, let me just slip this in. The GPS satellites orbit higher than like the space station and other things that are in what we call low Earth orbit.
Low Earth orbit.
They're in like MEO, the middle Earth orbit. There's LEO, MEO, and GEO. Okay. If you have kids, maybe you name them that.
Yes. Leo, Mio, and Geo.
Low Earth orbit, middle Earth orbit, and geosynchronous geo orbit. Okay,
Right.
So the geosynchronous satellites are like middle orbit. That is far enough away from Earth's source of gravity for them to have a measurably different space-time condition.
Oh.
So that their clocks tick faster than our clocks on Earth's surface because they're farther away. And so remember I said the more intense the gravitational field is, the slower time ticks. So they're farther away. Their time ticks faster relative to us.
Wow.
But we get precise timings from geosynchronous satellites. So how does this work? We pre-correct the time signal from the GPS satellites to compensate for Einstein's general theory of relativity so that by the time the time reaches us, it's been properly corrected and it matters to us and our space-time continuum, not the one that's in middle Earth orbit.
Oh my goodness.
So GPS couldn't work as accurately as it does.
However, wait a minute.
What?
I'm sorry, just for me. You would have to have a standard in order to pre-correct something.
You know the rate at which its time is speeding up because you can calculate what the gravitational field is up there.
There you go. There you go. Okay.
And once you calculate that, then you do and you say, oh my gosh, the formula works. Einstein was right. Right. This is not just something on a high theory, hypothesized that may or may not be true. It is true.
I just want to be there when that phrase is uttered. Oh my God, Einstein was right.
Yeah, these aren't just cult heroes that we wish they were right. These are real. This is real. Okay, this is the real universe we're talking about here. Okay, so now watch. Let's keep going faster and faster. Okay. Let's go half the speed of light, three-quarters the speed, 90% the speed of light, 99% the speed of light. Time is ticking slower and slower and slower. For you, you will watch the whole future history of the universe unfold in front of your eyes as fractions of a second go by for you. As you go 99, there's a formula for this, of course, but 99.9, 99.99% the speed of light.
Because you're the observer of that.
For
you, your time has slowed to the point where as you observe the things that are not moving at the speed of light, you see them
speeding.
Basically,
correct.
You see
speeding
them
up.
Unfold.
Correct.
Boom. God.
Correct.
That is insane.
Okay. So now watch.
Oh my God. Wait.
No, watch. Okay.
Wow.
So I didn't even get to the part where I lose sleep.
Okay.
That's what happens. By the way, there are particles that decay. You've heard of like radioactivity, right?
Yes.
It's one part, it decays and becomes another part and releases often deadly energy.
Yes.
Okay. Radioactivity. All right. Some particles, let's take, for example, the proton or the muon. One of these it decays in like 6 minutes when it's left out in the wild. Okay, when it's not part of an atom.
Okay.
When it's not in captivity, I forgot which of these, but it doesn't matter for my example. Decays in like 6 minutes. Okay. What happens if you take that particle and speed it up in a particle accelerator? So you take a community of these particles, speed them up, calculate. Wait a minute, the internal wristwatch on these clocks says they should live longer, and sure enough, their decay time takes longer.
Wow. That's, oh my God.
Yes.
Oh, wow.
Yes.
And that becomes living proof of what Einstein said.
Yes, because we can't go half the speed of light.
Right.
But you can accelerate a particle to do that.
Yes.
It's an internal built-in clock that decays after a certain amount of time, and there they are taking longer to decay in the exact amount that Einstein predicts.
That is genius.
So we don't make this stuff up, okay?
Yeah.
Yes, it is genius. It's like triple genius. All right. Now, let's take this to an extreme level.
Right.
Let's go so fast that we're going the speed of light itself.
Right.
Well, we can't do that because we're made of material substance, and there's no way to do that. But there are things that travel at the speed of light. And what is that?
Those would be photons.
Yes. Thank you. Those would be, like your finger gesture. That would be, I would say, what travels at the speed of light? Light does.
Yeah.
Okay.
I was about to say light.
So if photons had a clock, the clock would never tick.
Nice.
Which means when I go to a mountaintop, as I did in graduate school, to observe the center of the Milky Way galaxy for stars that emitted their light 30,000 years ago, traveling through the gaps of interstellar space, and they move through space, come through Earth's atmosphere, they come down into the telescope, they reflect, go back to my detector, and land on my CCD chip. That photon, when it was born, the star that emitted it was detected at my telescope in the same instant,
Wow.
according to the photon itself.
Live fast, die hard.
The photon has no knowledge
No knowledge.
of that trip
Right.
because time did not exist for it.
Oh, that's great.
And I'm saddened that many of these photons like hit people tanning on the beach, you know, and
They're
imagine
very
traveling
sad.
30,000 years and land on someone's buttocks.
Yep,
when
very
you could've
sad.
And with the telescopes I collected, I'm now decoding the nature of the universe. And some photons go right on by Earth and are still moving, but they have no internal time clock.
Wow. And they're just traveling through like, I hope when I'm born I hit a telescope.
Bam! You're born and you hit a telescope. Yeah, that would be interesting. But what I want to be when I grow up, or,
Right.
you know, or the instant I am emitted, where am I going to be
Where
absorbed?
would I like to be? Yeah.
Right. And so, just the idea that light can move across the universe and have no and not age. This is a fascinating fact to me.
Wow.
So, yeah.
That is more than fascinating. That is,
Yeah.
I mean, that's mind-boggling.
Yeah. So that is light, the age of light. It's like it doesn't age at all.
I am convinced that all of you guys secretly microdose and smoke weed. That's
That's another episode. That's what I'm saying.
Another episode.
All right, Chuck, we're calling it quits there.
All right.
All right, mysteries of light and time. Neil deGrasse Tyson here. Keep looking up.
What is time? In this channel, we've talked a lot about time. As black holes warp space around them, we've learned that time slows down. We've discovered the time-influencing effects of gravity, and even how the James Webb Telescope can peer through time to the distant past by taking advantage of the fixed speed of light. All this makes sense so far, but what actually is time? You can't taste it, touch it, or feel it, yet time has an unstoppable influence on us, and is pushing us forward whether we like it or not. Doesn't something that impacts everything we do deserve some additional understanding? I'm Alex McColgan, and you're watching Astrum. And while this is an area that scientists have many theories about, I'd like to share with you today one model that might help you understand this mysterious concept that is ticking all around us. By the end of this video, we are going to have a possible explanation for why time slows down as velocity increases, and why shapes warp when undergoing velocities close to the speed of light. This video is a collaboration with my brother, based on recognized scientific theory, where we have taken scientific concepts and combined them into something you may not have seen before. But before we get to that, we have to begin with one foundational idea. Time is actually another dimension. Now, before you double check that you haven't logged into some sci-fi channel by mistake, let's discuss what I mean by dimensions. While in popular culture, different dimensions are often described as parallel worlds that are very similar to ours, yet subtly different. In this context, when we talk of different dimensions, we are referring to the dimensions of space, as in three-dimensional space, or 3D space, which may be far more familiar to you. This is by no means trivial though. 3D space is all around you. It is the around you, and is very relevant to our topic. Let's begin by making sure we understand the 3Ds and the relationships between them before we add the fourth D. Broadly speaking, 3D or three-dimensional space simply refers to space that can be measured in three different perpendicular directions. The perpendicular nature of these dimensions is important, but we'll get to that later. Three-dimensional space is usually described as having height, width, and depth, and they all have 90-degree angles between them. Simply put, objects like us that exist in 3D space can move left and right, up and down, and forwards and backwards. We are comfortable with this kind of space. Using this as our basis, it becomes much easier to imagine what we mean by 2D space and even 1D space. To move from one space to another, all we need to do is remove or add an extra dimension of measurement or movement that must be a 90-degree angle from all previously existing angles. So, 2D objects move in a plane that's bounded by the X and Y directions, or the X and Z directions, or the Y and Z directions, but not all three at once. 1D objects can only move either along X, or Y, or Z. Imagine a person who lived in such a 1D world. Their whole existence would be found either moving one way or the other. All of reality would exist either to the left or to the right of them, and would appear as a singular dot. They could not move or see in any of the other directions, and probably could not even comprehend such directions as even existing. Photons whizzing by them would only be visible if they entered the singular line that was a 1D person's whole area of existence. Now, adding extra directions of movement is what's needed to move things up from 1D to 2D to 3D. So, in theory, we can predict what we need to do if we were to jump to 4D. However, here we hit a snag. While it's easy to draw a line that's perfectly perpendicular to a single other line, or to draw another line on top of those lines that is perpendicular to the two previous lines, how would we draw a fourth line that's perpendicular to all three? Surely such a thing is impossible. Well, within 3D space, such a thing is impossible. The best we can do is draw approximations. For instance, it's possible to draw an approximation of a 3D shape on 2D paper by doing something like this. These lines are all two-dimensional, but we look at this and our brain recognizes that this is a picture of a 3D shape. So, in the same way, we could probably do something similar to what a 4D object might look like using just 3D lines. Mathematicians have attempted to do this, although their results tend to be a little confusing. Although this is mathematically sound as a basis for a 4D object, I personally don't find my understanding of 4D space deepened by looking at it, so I won't focus on it in this video. There is some evidence, however, that a fourth direction exists, and we are moving along it right now. That fourth direction, or dimension, is time. Einstein predicted this connection when he linked space and time into one unified space-time in his theories of relativity. According to him, time and space are two parts of the same thing. To me, this connects with 4D space very nicely. Just as there is no real difference between the Z and the X or Y directions, so too would there not be any difference between time and space if time is just another direction, albeit one that we can't see. And time is important. Without time, our 3D space wouldn't move. It would perpetually be in one state, because it's time that allows us to move about in it. But why can't we see it? Why can't we look in the direction of time? To explain this, let's look at the difference between the different dimensional spaces. We best notice this when we consider what 2D objects might look like if they were to move around in 3D space. This is where we start to delve into the model. Let's begin by visualizing a standard 3D space. But because we want to eventually see all of space and time in one model, let's cheat a little. Let's compress all of 3D reality as we know it into a flat, two-dimensional place. In this plane, let's make that our XY plane, which we will label space, which frees up the Z dimension for time. In this model, all 3D people are now just 2D. A 2D person could exist and live their lives in the place marked space at the bottom of our chart. However, by moving them up on the chart at a constant rate, they are also moving through time. Let's for ease and convenience say that the top of our diagram is the future, while the bottom is the past. So the higher up our 2D person goes in this diagram, the older they get. As we don't seem to have a whole lot of control over our ability to travel through time, let's imagine for a second that our 2D person travels upwards at a constant rate, as if there is some consistent force or wind at play pushing them upwards towards the future. Sadly, we cannot slow down time for ourselves simply through willpower, no matter how much we might want to do so. However, it is misleading to say that we can't change it at all. The faster we travel in space, the slower we travel in time. This is one of the guiding principles of Einstein's relativity. This model can express this idea through the power of vectors. As our 2D person tries to move to their left or to their right, their vector of travel changes. While traveling at a fixed rate, like a sail on a ship catching a breeze, we can only go as fast as the wind takes us. So the vector coming out from their front must always remain the same. To travel the fastest through time, our 2D person must orient his vector completely in the future direction or upwards. However, if they are to travel any amount in either direction to their sides, they can only do so by pointing their vector away from their direction of travel. They have motion in the X direction now, but they have done so by reducing their motion in the Z direction. They are moving through space, but at the cost of moving a little slower through time. Taking this to its furthest extreme, our individual has completely flipped on their side and now only has motion in the direction of x and none in the direction of z. They have velocity in space, but not time. So I suppose this implies our vector is the speed of causality, or the speed of light. If this is the speed we're talking about, then moving at low speeds through space would not have any noticeable difference in our speed through time. We'd have to go really fast before we started to notice anything. The vector still mostly points upwards. An interesting result of this model is that, from the 2D man's perspective, nothing has really changed. He has his own view of what reality is. For him, the vector coming out of his chest is still time. The dimensions of the plane he's lying flat on is his space. To him, it's the rest of the universe that's gone a little weird, but he himself is perfectly normal. However, once he reorients himself, it is clear that the rest of the universe has moved on without him. This is clearer if we add a second 2D person. Initially, both of our individuals do not move in space. All of their vector is pointing in the direction of time. Nothing that strange seems to happen so far. However, if our stick man on the right turns and vectors at near the speed of light for a bit, then reorients himself, while the second 2D man on the left just stays where he is, it becomes clear that our 2D men have not moved at the same rate through time. Assuming that our two stick men can somehow still see each other, let's imagine that they somehow project an image of themselves onto the other person's space plane. They immediately notice that there is a difference in age. The one who traveled at the speed of light did not advance so quickly through time as the other, who remained stationary and so is younger. But why do we find this model so compelling? Well, it is because of what those projections would look like during changes in direction. From the point of view of the first stick man, initially the projection of their friend seems fairly normal. However, as they start traveling very quickly in space, and their vector oriented in a direction away from time, a 2D shape reveals its inherent flatness. And from a face-on perspective, it goes from this to this. The speedily traveling stickman appears to flatten, with an effect that's more pronounced the faster they go, and the flattening takes place in the direction of their travel. The stickman who remains stationary might wonder at the strange change that is occurring to their friend, never comprehending that it represents a reorientation of a 2D figure in 3D space. Now, what captures my imagination about this is that this same thing happens in real life. According to Einstein's theories of relativity, objects traveling at great speeds in 3D space would appear from an external observer to flatten in the direction of their travel. This squishing effect happens exactly in line with this model, and is to do with time dilation. However, from the person who's traveling's perspective, they do not flatten, but it is the rest of the universe that warps. I talk about this in greater depth in another video of mine, where we can see the effects of spatial warping in a computer model. From their perspective, everything would stretch at the edges of their vision, while their destination would seem further away, which is again what this model would predict. The only difference is that in this model we're just exploring a 2D object stretching. So the stretch is only in one direction, while in real life it's 3D, which means it stretches in two directions instead. But that is what you might expect as you turn away from our conventional 3 dimensions and start orienting yourself away from time. But if this is correct, so what? Why does it matter? If time is truly a direction, then it deepens our understanding of the universe. It also raises more questions. What is the force that pushes us ever forward in time? Why does it seem that we can never move against it? Although in this model there is no reason why a vector could not point downwards, in real life that doesn't seem to ever happen. This model also answers the question of, if time is a direction, what is our shape in time? Does part of us protrude into the past or into the future? According to this model, that does not happen. We are flat pancakes in the 4th dimension, pennies that look round when you look at us head on, but revealing our thinness when we turn away from you. That's a strange thought, but it may just be true. This might explain why we are unable to see through time. We just don't extend enough in that direction for it to be visible. Your form might be quite different than you first thought. Of course, this model is just a theory of ours, although we have tried to base it on scientific observations and conventional theory. But what do you think? Does this model help you make sense of time as a 4th dimension? Please leave your ideas in the comments below on the nature of time and what it might actually be instead. I hope to explore more strange concepts like this in a new series called The Unseen World, where I want to explore the shape of reality around us. While it's normally invisible to us, the shape and dimensions of the universe can explain why things are the way they are, and I'm excited to explore it with you. If you are interested in it, let me know. I'm very pleased to finally show you something that's been in the works for a while. I've been working together with Stuart McPherson and the Don Hanson Foundation to produce a book. It has already been sent to thousands of schools around the world to hopefully help school children develop a love for space. And now they're available to you too. The focus of this 160-page book is the solar system and contains thousands of facts about the different celestial bodies found there. And what I actually love most about the book is the print quality combined with the images. Somehow these images just look so good when printed out compared to seeing them on a computer screen. I spent hours finding the very best images to include, and I'm very proud of the finished product. The initial sale is a limited edition of only 175 books, so it's really while stocks last. And they will include a signed card from me and a serial showing your unique number. I really expect these to go fast, so don't delay and check my store link below. Thanks for watching. I hope you learned something new today. If you did, consider subscribing for more. Liking and sharing also really help. Another way to support is to become a patron or member. If you'd like to see your name added to this list, check the links below. All the best, and see you next time.